Hello everyone. Today I'm going to talk about how memory and caches interact with each other. Throughout the semester, we have been talking about how processors manipulate data in order to achieve a desired outcome. But now we are going to learn how data is handled in order to be stored more efficiently and used more quickly. This pyramid is a great way to visualize our data hierarchy. These two levels represent caches, and these two levels represent memory. The reason this image is so useful is because we can see that each level of data storage holds more information than the next. This secondary memory is able to store more information than this main memory, which is able to store more information than this L2 cache, which is able to store more information than this L1 cache. We would like, ideally, for all of our information, all of our data, to be in this L1 cache right here, because this cache is what directly interacts with our processor. Caches and memory are the same thing in the sense that they both store data. However, caches utilize what's called SRAM, or Static Random Access Memory. Main memory and secondary memory utilize what's called Dynamic Random Access Memory. The differences between these are that the SRAM is very fast. However, it's also expensive and requires lots of power. Conversely, our DRAM is very slow, but it's also cheap and doesn't require nearly as much power. For the purposes of this class, though, the only thing we need to worry about is that when accessing memory, it's very slow. And when accessing caches, it's very fast. To measure just how fast our processor is able to grab information is by examining the hit rate. The hit rate is the number of times our processor is able to correctly grab information from this L1, this level 1 cache, also known as the upper level. Just as important as the hit rate is the miss rate. The miss rate is the number of times that our processor needs to go to a different level in our memory hierarchy in order to grab the right data. The miss rate is calculated by taking 1 minus the hit rate. Another way to measure efficiency is to calculate the hit time. This is the time that it takes for the processor to access this upper level of our data hierarchy, minus the time for the processor to determine whether or not the data in this L1 cache is the correct data that we need to use. Just as important as the hit time is the miss penalty. The miss penalty is the time that it takes to replace a block in the upper level, plus the time to deliver the block to the processor. So if there is data that our processor needs to access, but it's not in this L1 cache, then we have to go and find it somewhere else. If it's in our L2 cache, that's great, but we need to be able to take that information and put it back into the L1 cache and then take it and give it to the processor. That is what the miss penalty is calculating, the time that it takes to do these two steps. So once we actually find information in our memory, we need to be able to store it in the cache in an organized fashion so we can access it quickly. One of the ways is called directly mapping. This involves taking an address from memory and storing it to a corresponding location in the cache. Because we have a limited amount of space in our cache, we're going to have many different addresses from our memory mapped to the same location in our cache. To know which memory goes into which part of the cache, we have to look at the addresses of all the pieces of memory. These last two bits are don't cares to accommodate for the data offset into each new address. These middle two bits are going to be our index. They will tell us where this piece of memory is going to go in this cache, because obviously memory and caches are not color-coded. These remaining two bits are called the tag. The tag is going to let us know if we're going to be using this red block or this red block in our cache. This also will let us know if we need to update our valid bit. The valid bit will let us know if this data is up to date. It checks this by looking at the tag. If the tag that is in the cache matches a tag for the data that we request, then we know that this is the correct data to use. This is an example of taking memory and putting it into the cache. We're going to be accessing memory address 0, 1, 1, and then 4 in this order. So these 4 blocks are going to be our caches at the different stages of memory access. And this is going to be just a reference so that we can look back and know why memory 0 is going in this particular spot of the of our cache and not, say, in this green spot right here. So our cache always starts out completely empty, and then as we access new memory, we will fill it in with the corresponding locations from as indicated by the index. That's why this memory 0 is going into this first block in our cache, because its index indicates that it goes into spot 0, 0. We are also going to bring along the tag, and we're going to place that tag right here so that we know that we're using this block of memory and not this block of memory, because the indexes are exactly the same, but the tags are completely different. So next we're going to access memory address 1, and we're going to take this block of memory and we're going to put it right here, because its index says to put it in slot number 1 and not slot number 0. And we're going to do the same thing as we did with the first memory, and we're going to bring along its tag, which is right here, and it's 0, 0, and we're going to leave it right next to this block of memory. And just like because we had to fill in our cache with memory 0, by putting in memory 1, we have another miss. So we have 2 misses in a row now. But next, when we access memory address 1 again, we already have it, and so we finally get our first hit. Next, we're going to access memory address number 4, and its index is telling us to put it in spot 0. But we already have something in spot 0, so is it the right one? Well, to know that, we look at the tag. Its tag says 0, 1 and not 0, 0. Therefore, we know that this is the incorrect data to use. And so we're going to take this memory 0 and take it out, and we're going to take this memory 4 and put it in. Unfortunately, because we had to replace memory 0 with memory 4, it caused us to have another miss. But this is going to be the end result of what our cache is going to look like after we access all these different memories. But looking at the end result of this cache, we see that only 2 different spots are used. And we have these 2 other slots that are available still and haven't even been touched. So how can we make up for this empty space? How can we utilize it somehow? For this, we now move on to what is called a set associative cache. The only difference between a direct mapped cache and a set associative cache is that these individual blocks in memory can be stored to different locations in the cache. So, if we need to access this memory right here, but this spot is already taken, instead of replacing this one, we can just bring it down here and put it into this other location in the cache. Therefore, we still can maintain our hit if we need to use this data later on. And we can still update the cache and take advantage of this unused space. You do need to notice, though, that the index has changed and the tag has also changed. The index has decreased in size and the tag has increased. But the purpose is still the same. The index is still telling us where this block of memory needs to go in the cache, whether or not it goes in this spot or in this spot. This top pair will be called way 0 and this bottom pair will be called way 1. So here's the exact same example as before, except now we're going to be using set associative cache. We're still going to be accessing memory 0, 1, 1, and 4. Just like before, the cache is completely empty until we need to access this memory. So when trying to access memory 0, we see that its index is a 0. So we put memory 0 into this first spot, and we bring this tag over, this 3 zeros, and put it right next to it, just like before. Unfortunately, again, we still get a miss. When we try and access memory 1, we do the exact same thing again. We see that memory 1 has an index of 1, and so we put it into this second slot right here. We also bring the tag over and put it right next to it, just like with all the other memories. When we try and access memory 1 again, we already have it, and so we get our first hit. Now is when things change. Just as I mentioned before, because we're going to now use a set associative cache, whenever we try and access memory 4, instead of replacing it with memory 0 in way 0, we can move it to way 1 and put it in this slot down here. This way, we don't have to replace memory 0 in case we need it for future reference, and we take advantage of this other space down here. Unfortunately, though, it is still considered a miss. There is a third type of organization called spatial locality. What this does is take blocks of memory and put it into the cache. So it's going to take, instead of just one piece of memory, it'll take several. In this case, for this example, it'll take 2. The benefits of this being is that if there is a program that needs to access sequential bits of data, then we can just take all of them at once and put them directly into the cache and have them ready for the first time that we retrieve information. An important consequence of this, though, is that if we need to access, say, just this red block down here, then we need to get rid of both of these pieces of memory and then take both of these pairs of memory and put them back into the cache. We cannot just take this red block and replace it with just one of these red blocks. This setup makes our system slow when loading data into the cache, but it makes it really quick to access it once it's in there. It also makes it really slow to get rid of the data. Here now is the same example, but we will be using spatial locality in order to organize our cache. Again, our cache starts out completely empty, and then we start accessing information. So we go and retrieve memory 0 and place it in the cache. But this time, instead of just taking memory 0, we now take memory 1 as well. Now, when we need to access memory 1, we already have it in the cache, and so we get a hit. When we try and access memory 1 again, we get a second hit. Now, when we try and access memory 4, we're going to take both memory 4 and 5 and place them also in the cache. So that's how memory and caches interact with each other. I hope I was helpful. I hope that y'all learned something. Good luck on the exam. Hi, Dr. Sprinston.